We are very happy to introduce Helen Jenne from the University of Oregon, who is going to be talking to us today about the combinatorics of the double dimer model. Take it away.
Great. Thank you so much for coming, everyone. Today I will be, in this pre-seminar, I'll be talking about the dimer model and co-condensation. So I'm going to start by defining a dimer configuration, and then I'll spend most of my time talking about co-condensation, which is a powerful technique for enumerating dimer configurations. And I'll conclude by defining double dimer configurations, which are the objects that I'll be talking about in my seminar talk. And please feel free to interrupt with questions at any point. Okay, so just beginning with some definitions. A graph is bipartite if you can divide its vertices into two sets, a set of black vertices and a set of white vertices, so that every edge connects a black vertex to a white vertex. So shown on the slide is an example of a bipartite graph. And throughout this talk, all of our graphs are going to be finite bipartite planar graphs. So a graph is planar if it can be drawn without any edge crossings. And so now a dimer configuration, which is also called a perfect matching of such a graph, is a collection of edges that covers each vertex exactly once. So shown is a grid graph and a dimer configuration of that graph. And throughout this talk, we'll assume that the number of black vertices is equal to the number of white vertices, because if that's not the case, then the graph doesn't have any dimer configurations. So as combinatorialists, some immediate questions we might have are, given a graph, how can we count all of its dimer configurations other than just drawing them all out? Or another natural question to ask is, for a certain family of graphs, such as like grid graphs or honeycomb graphs, are there nice formulas for the number of perfect matchings of these graphs? So in the 1960s, Castellan showed how to count dimer configurations of planar graphs. In the bipartite case, he proved that there's a matrix K with the property that its determinant is equal to the number of dimer configurations of the graph. And when the graph is not bipartite, there's a matrix with the property that it's Pfaffian is the number of dimer configurations. But today we'll just be talking about the bipartite case. And then he used his techniques to give an explicit formula for the number of dimer configurations of an m by n grid graph. So I'm not going to really talk about his work much today at all. I just wanted to show this because I think it's very surprising. It's not even obvious to me that this formula would work out to be an integer, for instance, but it counts the number of dimer configurations of grid graphs. So what I'll be talking about today, rather than Castellan's work, is a technique discovered by Eric Kuo that is a really useful technique for counting dimer configurations. But for more information on Castellan's work and just for other techniques for counting dimer configurations, I'd like to recommend the paper Enumeration of Tilings by Jenne Prop, which is a really nice survey. Okay. So now moving on to Kuo's work. So we're going to let M of G denote the number of dimer configurations or perfect matchings of G. Just a disclaimer, I'll probably be using the word dimer configuration, perfect matching interchangeably. I hope that's not confusing. When I'm talking about Kuo's work, I tend to use the word perfect matching because that's like what he uses. So that's what I'm used to seeing in his work. Anyways, so Kuo proved that the number of perfect matchings of a graph satisfies a really nice recurrence. So if you have a graph embedded in the plane, like this grid graph shown, and you have four vertices, A, B, C, and D, that appear in a cyclic order on a face of a graph. So in this example, A, B, C, and D are on the outer face, but that doesn't necessarily have to be the case. They can be on any face of the graph. And if you assume that A and C are both black and B and D are both white, then the number of perfect matchings of G times the number of perfect matchings of G with those 4 vertices removed is equal to the sum of products of perfect matchings of modifications of G as shown. So notice—
Helen, there's a question in the chat asking what a face is. Clarification on that.
Oh, so whenever you when you draw a graph in a plane, the edges separate the plane into regions. So like this would be a face. Is that clearer?
Sorry, what I meant is, are bigger rectangles, those are made of several squares, are they faces too?
Yeah, like all of these. So this graph has 10 faces. It has these 9. Oh, they mean like these? No.
No, you've answered it with the number 10. Thank you.
Okay, great. Okay, excellent. All right. Right. So this is Quo's recurrence. And then what I want to point out is that each term on the right-hand side comes from deleting one black vertex and one white vertex in all possible ways. And remember that we wouldn't expect to see terms where we have deleted 2 black vertices, because if you delete 2 black vertices, then there aren't any perfect matchings. Before I move on, are there any questions about what this theorem says?
And if you have questions, you can turn on your microphone or use the chat.
Okay, so I'll keep going.
There was one question in the chat asking whether clockwise versus counterclockwise order matters.
No, that wouldn't matter. Yeah, great. Okay, so I should note that you can prove this theorem using linear algebra. You can use the Castellan matrix and an old identity called Dodgson condensation. But the proof I'm going to talk about today is Quo's proof, which uses a technique he calls graphical condensation. And that involves superimposing 2 matchings of bipartite graphs, and then showing that the resulting configuration that you get can be decomposed into matchings of other graphs. And so what we're going to do is, if we let script m of g denote the set of perfect matchings of G, we're going to show that the Cartesian product of m of G with m of G minus a, b, c, d has the same size as this set, which I'm not going to attempt to say out loud, but you can all read. Are there any questions about anything I've said so far before I move on to his proof? Okay, great. So we start by superimposing a perfect matching of G with a perfect matching of G with A, B, C, and D deleted. And what we get is a multigraph. So the doubled edges I've just denoted in purple. And notice that every vertex in this multigraph has degree 2, except for the vertices A, B, C, and D. And so just to give another example, if say we start with a different perfect matching of G, we get another one of these multigraphs. And the thing that I want to point out is that both of these multigraphs have 2 paths with endpoints A, B, C, and D. So this first one has paths from A to B and C to D, and the second one has paths from A to D and B to C. And just notice that it wouldn't be possible for us to have a configuration with paths from A to C and B to D, because those paths would have to cross, and then we would have to have a vertex with degree 4. So we're always going to be in one of these two situations. So to prove his theorem, what Quo does is he lets H be one of these multigraphs on the vertices of G, so that every vertex has degree 2, except for A, B, C, and D. And then what he shows is that H can be partitioned into a matching of G and a matching of G minus A, B, C, D in 2 to the C ways, where C is the number of cycles in the graph. So just to mention, in case there's any confusion, a doubled edge doesn't count as a cycle. And then we're also going to show that H can be partitioned into either a matching of G with A and B deleted and a matching of G with C and D deleted, or a matching of G with A and D deleted and a matching of G with B and C deleted. But it can never, but it has to be one of those two. It can't be both. And that either of those partitionings can be done in 2 to the C ways. So that's what we'll show. So then now on to the first claim. So we'll start by considering the path from A to B. So we want to partition this graph H into 2 matchings, and so the edge that's incident to A has to go into the matching of G. And then, since whenever you have a perfect matching, 2 edges can't share a vertex, the next edge in the path has to go into G minus A, B, C, D. And we continue to alternate which matching we're putting the edges and the paths into. And then the thing that we have to check is that when we reach the end of our path, when we get to the vertex B, it better be the case that the edge we put into that this edge needs to be red, right? It has to go into the matching of G. But that's always going to be the case because of the assumption we made that A and C and B and D are different colors, right? Since A is black and B is white, every single path from A to B will have an odd number of edges.
And there's been another question in the chat asking, is Quo's condensation basically a 3-term Plucker relation? And there's been some discussion.
Yes, it is. So there's a nice a paper by David Spire about that. I think the paper is called Variations on a Theme of Castellan or something, and it's a really short, nice paper, and it explicitly proves Quo's theorem as by using a Plucker relation. Great. Okay. Yeah, great question. Okay, right, so where was I? So we were talking about this path from A to B, and we partition the edges so that the red edges are going into the matching of G and the blue edges are going into the matching of G minus A, B, C, D. So then we can deal with the path from C to D in the same way, although in this case that path just has length 1. And then our doubled edges, we just put 1 edge into each matching, and then finally we have our cycle. And now, since G is bipartite, all the cycles have even length, so we can always just alternate which edges of the cycles we put in the matching. But we're going to have a choice, right? We can either put the vertical edges into the matching of G, or we can put the vertical edges into the matching of G minus A, B, C, D. So that's where this 2 to the C factor comes in. Okay. So that's the proof of claim 1, unless there are any questions. We'll move on to the second one. Okay. So then remember from earlier, we said that that we're always going to have paths from A to B or C to D, or paths from A to D and B to C. And which of those situations we're in determines whether H is partitioned into a matching of G minus AB and a matching of G minus CD, or into a matching of these other two graphs, right? And the reason is because we saw in the previous slide that all paths have odd length. So that means that the matching that we put this edge incident to A into is going to be the same matching that we put the edge incident to B into. So that means that in this case, we're only going to be able to partition this graph into a matching of G minus AB and a matching of G minus CD. And similarly, if we have a graph with paths from A to D and B to C, we're only going to be able to partition it into a graph, into a matching of G minus AD and a matching of G minus BC. And then the rest of the argument's the same. Doubled edges contribute to both matchings, and for every cycle, you have a choice of how to partition edges. Great. So that is the proof of Quo's theorem. Are there any questions?
So I have one. So far, I don't think you have used the planarity other than to argue that a path from A to C must always cross a path from B to D. Is that the only thing you use from the planarity?
Oh, well, you need to use the planarity to even sort of have his statement make sense, because you need it to be planar in order to talk about faces. You need a planar embedding in order for his theorem statement to really, I think, make sense.
But if I just have four vertices A, B, C, D, and I have this one thing that I know, any path from A to C crosses any path from B to D, is that enough for the theorem?
I don't think so. But I would have to think about it more. Yeah. Yeah. So I'll think about that more, but I don't think it's enough. I think you need planarity. So I'm gonna move on. So I said that this was a powerful technique for enumerating matchings, and the reason is because we've basically proven a recurrence. So then in some cases we can use this type of recurrence and induction to then prove like a closed form for the number of matchings of a particular type of graph. And an example of this is the Aztec diamond theorem. So an Aztec diamond of order n consists of 2n center rows of unit squares of length 2, 4, 6, and so on, all the way up to 2n, and then back down 4, 2. So shown are Aztec diamonds of order 2, order 3, and order 4. And it turns out that there's this really nice formula for the number of ways to tile an Aztec diamond with dominoes. So shown on this slide is an Aztec diamond of order 4 and a domino tiling of it. And in 1992, Elkies, Kuber, Berg, Larson, and Propp proved that the number of domino tilings of the order n Aztec diamond is 2 to the n times n plus 1 over 2. And since then, there have been a bunch of proofs of this theorem, and Quo proves it using his graphical condensation technique. So maybe if you haven't seen this before, this might seem a little bit funny that I was talking about perfect matchings of graphs, and now I'm talking about domino tilings. But there's a really nice connection, which is that if you have a domino tiling of a region of squares, that's equivalent to a perfect matching of its dual graph. So if you have a region of squares, you obtain the dual graph to that region by just putting a vertex in each face. And then there are edges between vertices whose corresponding faces share an edge. And then each domino tiling has a corresponding perfect matching, like shown in this example. So Quo uses the same technique of superimposing matchings to show that that the number of matchings of an order n Aztec diamond graph times the number of matchings of an order n minus 2 Aztec diamond graph is equal to 2 times the square of the number of matchings of an order n minus 1 Aztec diamond graph. And so he does that. He does this in the way you might expect based on the proof of the previous theorem we saw. He superimposes an Aztec diamond of order n minus 2 and a perfect matching of an Aztec diamond of order n, and then shows that you can then break those apart into perfect matchings of Aztec diamond graphs of order n minus 1. So that's a really nice application of his work. Any questions at this point? Okay, great. So then something else I wanted to mention is that Kuo's work also holds for edge-weighted graphs. So whenever you have a graph, you can assign a weight to each edge. So these weights can be real numbers or they can be formal variables. And if you have a perfect matching of a graph, the weight of a matching is just the product of its edge weights. So just to give an example with this a small graph, this graph has 3 edges with weights x, y, and z, and then the edges that aren't marked, you should just assume have weight 1. And the weight of the matching shown is x, y, z because it's the matching consists of these 3 vertical edges. And then when we have weighted graphs, instead of talking about the number of matchings, we can talk about the weighted sum of matchings. So we can talk about the sum over all perfect matchings of the weight of each matching. And this is often called the generating function or the partition function. And then Kuo's theorem, and to just give an example, the partition function for this graph is xyz plus x plus z because we have 3 perfect matchings. The perfect matching shown in the example, the perfect matching consisting of the vertical edge x and these 2 horizontal edges, and the perfect matching consisting of the vertical edge z and these 2 horizontal edges. And then Kuo's theorem has a version with partition functions instead of numbers. So, and the proof is the same. Great. And then next, I wanted to define double dimer configurations because that's what I'll be talking about during my seminar talk, and also just because we've already seen them. So the proof of Kuo condensation involved these multigraphs, right, where each vertex had degree 2, except for those 4 vertices A, B, C, and D. And those were examples of double dimer configurations on graphs with 4 nodes, A, B, C, and D. And in general, given a graph G, you can fix a set of special vertices called nodes on the outer face of the graph. And then a double dimer configuration is a subgraph of degree 2 at the internal vertices and degree 1 at the nodes, except for possibly having some doubled edges. So equivalently, you can think of it as a configuration of L disjoint loops. And so loops are what we were calling cycles earlier. Doubled edges and paths connecting the nodes in pairs. So for every double dimer configuration has a planar pairing of the nodes. And just like the weight of a matching is the product of the edge weights, the weight of a double dimer configuration is the product of its edge weights times 2 to the L, where L is the number of loops in the configuration. And that 2 to the L factor comes from what we saw in Kuo's proof that you can decompose a double dimer configuration into 2 dimer configurations, but when you do that, you have a choice whenever you have a loop for how to do that decomposition. Okay. And then something I wanted then to mention. So just like Z D of G was the weighted sum of dimer configurations, we use in notation Z D D sigma Gn to denote the weighted sum of all double dimer configurations with a particular planar pairing. And in Kuo's proof, it was the following identity was sort of implicit, that the number of double dimer configurations on a graph with 4 nodes with the pairing 1, 2, 3, 4 is equal to the product of dimer configurations on the product of the partition function for dimer configurations on the graph with 1 and 2 removed times the partition function on the graph with 3 and 4 removed, right? And that's because this double dimer configuration can always be decomposed into these 2 dimer configurations. And similarly, it was implicit in this proof that the partition function for double dimer configurations with this planar pairing can be written as a product of partition functions for dimer configurations. And if we define this quantity xij to be the partition function for dimer configurations of gij divided by the partition function for dimer configurations of G, then we can write these 2 equations as this quantity that almost looks like a probability, because it's the number of double dimer configurations with a particular pairing divided by this quantity that's sort of close-ish to the weighted sum of all double dimer configurations, is equal to this product x12, x34. And I mention this just because Kenyon and Wilson, who initiated the study of the double dimer model, considered graphs with an arbitrary number of nodes, and they showed that these quantities, which they called normalized probabilities, are always polynomials in these quantities xij. And so the smallest sort of example of their theorem is equivalent to sort of this work by Kuo, but then they proved it in much more generality, and that's something I'll be talking about in my seminar talk. Right, so that's all I have. So thank you so much for listening.